If your base class has more than 3 levels of subclasses, you do not have an architecture, you have a liability. I have seen this exact thing in production iOS code bases. Every new feature meant climbing 4 levels of inheritance just to understand one simple question. Where was this property actually set? You tap into a bug. The loading spinner appears twice. A button is disabled when it should be enabled. A screen tracks the wrong analytics event. And then you discover the behavior is not in the screen you are editing. It is in a base class, or a base class of the base class, or an override that calls super, or worse, an override that does not call super. Today, we are breaking down why Swift's protocol-oriented model exists, where inheritance is still the right choice, and the decision framework I use during real PR reviews to stop inheritance chains from becoming architectural debt. By the end of this video, you will know when to use a protocol with default implementations, when to use a class hierarchy, and when both are the wrong abstraction. This matters even more now. In 2026, teams are shipping faster with AI-assisted coding. That is powerful, but it also means bad architecture gets replicated faster. If your code base has a bad inheritance pattern, Copilot, Claude, Cursor, and other tools will happily extend it. AI does not always know the pattern is bad, it only knows the pattern exists. So the architecture you choose becomes the architecture the tools multiply. If you are serious about writing Swift that scales beyond a 5-person team, subscribe. This channel is for engineers who want real trade-offs, not surface-level tutorials. Let's name the problem precisely. Inheritance gives you 2 things bundled together: shared implementation and a type relationship. That bundling is the source of most problems you have experienced with class hierarchies. When you subclass, you are not just saying, reuse this code. You are saying, this new type is a specialized version of the parent type. Those are not the same thing. At first, this looks harmless. A BaseViewController provides loading behavior. A profile screen inherits it. The code is simple, the team is happy. No problem yet. Then another screen needs form behavior. So we create FormViewController. Now check out ViewController inherits loading and form validation. Still not terrible, but the hierarchy is growing and the cost is starting to hide. Now payment behavior gets added, and a card payment screen inherits from it. At this point, the screen inherits loading behavior, form behavior, payment behavior, and UIKit lifecycle behavior. The class is not just reusing code anymore. It is carrying history. Now imagine a bug. The user edits a payment form, navigates away, comes back, and the app forgets their unsaved changes. You search in Card Payment View Controller, nothing. You search in Payment View Controller, nothing. Then you finally find this in Form View Controller. The property was reset in a parent lifecycle method. That is the inheritance liability. The code is technically reused, but the behavior is no longer local. Inheritance also creates hidden rules. Should the subclass call super? Must it call super before custom logic? Can it call super after custom logic? What breaks if it forgets? Sometimes the compiler helps. Most of the time, it does not. That contract lives in human memory, comments, or tribal knowledge. That is not a great place for important architecture rules. This is known as the fragile base class problem. A parent class changes, and subclasses break even though nobody touched them. The deeper the hierarchy, the more dangerous this gets. The base class becomes a shared global dependency with a nicer name. Everyone depends on it. Nobody fully understands it. Everyone is afraid to change it. This is where Swift's protocol-oriented programming model becomes powerful. Protocols separate the contract from the ancestry. A protocol says, this type can do something. It does not say, this type must come from this parent class. That is a huge difference. Instead of forcing every screen to inherit from BaseViewController, we can define a capability. LoadingPresentable. Any view controller that has a loading view can opt into this behavior. It does not need to inherit loading. It conforms to loading. That is the shift. Now, Profile View Controller still inherits from UI View Controller because UIKit requires that. But loading behavior is composed through a protocol. The class hierarchy stays shallow. The capability is reusable, and the screen only opts into what it actually needs. Analytics is a perfect example. A settings screen can track analytics. A SwiftUI view can track analytics. A coordinator can track analytics. A service can track analytics. These things should not all inherit from the same base class. They share a capability, not an identity. That is protocol territory. Here is a simple test I use in PR reviews. Can I name this thing with an able or ing suffix and have it make sense? Trackable, validatable, retrying, formatting, cacheable. That is usually a protocol, because you are describing what a type can do, not what a type is. Validation is another strong example. An email form and a password form both validate, but one is not a subclass of the other. There is no meaningful inheritance relationship here. A protocol expresses the shared behavior without forcing a fake family tree. Now here is where many videos lie to you. Protocols are not automatically better. They have costs. And if your team does not understand those costs, protocols can create a different kind of confusion. Not inheritance confusion, dispatch confusion, existential confusion, associated type confusion. When you use a protocol as a type in modern Swift, you usually write any protocol name. That is an existential. It means the concrete type is hidden behind a protocol value. This is flexible, but it can introduce runtime overhead because Swift may need an existential container and dynamic dispatch. Most of the time, this is not your bottleneck. But in performance-sensitive paths, like rendering thousands of rows, parsing large datasets, or tight loops, it can matter. If you do not need to store mixed concrete types together, a generic can often be better. The generic version keeps the concrete type known to the compiler. That gives Swift more room to optimize. So the rule is simple. Use any protocol when you need heterogeneity. Use generics when you want abstraction without erasing the concrete type. Protocols with associated types are powerful, but they are not always easy to use as simple values. For example, a repository protocol might define an associated entity. That makes sense. A user repository returns users. A product repository returns products. But now, you cannot always treat all repositories as one simple, any repository, without thinking carefully about what entity means. This is not a bad protocol. It is probably a good one, but it is not the same kind of protocol as LoadingPresentable. Associated types are great for modeling relationships between inputs and outputs, but they make the abstraction more advanced. So do not reach for them casually just to make code feel protocol-oriented. Protocol extensions can also surprise people. If a method is a protocol requirement, Swift can dynamically dispatch it through the protocol. In this example, log is required by the protocol, so the concrete implementation works as expected. But now look carefully. Log is not declared as a protocol requirement. It only exists in the extension. That changes the behavior. When you call through any logger, Swift may use the extension implementation because the method is not part of the protocol's dynamic dispatch contract. This is one of the biggest protocol extension traps. If conforming types are supposed to customize the method, put the method in the protocol requirement. This version is safer. The protocol declares the requirement. The extension provides a default. The conforming type can override the default. That is the pattern you usually want. Requirement in the protocol. Default behavior in the extension, custom behavior in the conforming type. Now let's be fair. Inheritance is not wrong. UIKit itself is built around inheritance. UIViewController, UIView, UITableViewCell, UICollectionViewCell, UIControl. You are not going to protocol your way out of UIKit's lifecycle. A view controller really is a specialized kind of UI view controller. A custom button really is a specialized kind of UI button. That is legitimate inheritance. This is a good use of inheritance. PrimaryButton is a UI button. It participates in UIKit's control lifecycle. It needs initialization paths. It needs UIKit behavior. Here, subclassing is not the problem. The problem starts when you use inheritance as a general-purpose code reuse mechanism for unrelated behavior. This looks convenient. Every analytics screen inherits from Analytics View Controller, but now Analytics is tied to View Controller inheritance. What happens when a screen already needs to inherit from another base class? What happens when a SwiftUI view needs the same tracking? What happens when a coordinator needs to track an event? This is not a type relationship. This is a capability, so inheritance is the wrong tool. This version composes the behavior. Home View Controller is still a UI View Controller, but tracking is a protocol. Now the same capability can be reused anywhere. No fake base class, no forced hierarchy, No inheritance just to share one method. This is also why SwiftUI feels so different from UIKit. SwiftUI does not ask you to subclass BaseView. There is no UIViewController style class tree for every screen. Instead, each view conforms to the view protocol. The framework composes behavior through protocols, generics, modifiers, property wrappers, and value types. That is protocol-oriented design at scale. In SwiftUI, instead of creating a base loading view, you create a modifier. Then any view can opt into the behavior. Profile view, .loadingOverlay, viewModel.isLoading. That is composition, and it is usually more flexible than inheritance. Here is the decision framework I use in real PR reviews. Question 1. Are these types sharing identity, state, and lifecycle? If yes, inheritance may be correct. Question 2. Are these types just sharing a capability? If yes, use a protocol. Question 3. Do I need shared stored state? If yes, a protocol extension alone cannot store it. You may need composition with a helper object. Question 4. Will unrelated types need this behavior? If yes, inheritance is probably wrong. Question 5. Will this abstraction make call sites clearer or just hide behavior? If it hides behavior, do not create the abstraction yet. Protocols can require state, but protocol extensions cannot store state. That matters. If you need shared mutable state, a protocol may not be enough. For example, retry logic might need current attempt, maximum attempts, backoff delay, cancellation state. That may be better modeled as a composed object. This is an important point. The alternative to inheritance is not always protocols. Sometimes the better answer is composition. Create a small object that owns the state, then inject it or hold it privately. Now the state is explicit, the lifecycle is explicit, and the type does not inherit behavior it does not truly own. So the real decision is not just protocols versus inheritance. It is inheritance for identity and lifecycle, protocols for capabilities and contracts, composition for reusable behavior with state. If you understand those three, your architecture gets much cleaner. Here is the kind of code AI tools often generate if your codebase already has this pattern. A massive BaseViewController. It handles loading, errors, analytics, navigation bar styling, view model binding, maybe keyboard behavior, maybe empty states, maybe localization. At this point, it is not a base class. It is a junk drawer. The refactor is usually not one giant rewrite. Start by extracting capabilities. Loading becomes LoadingPresentable. Errors become error-presentable. Analytics becomes screen trackable. Navigation becomes navigation configurable. You do not need to delete the base class on day one. You just stop adding new responsibilities to it. That is how you reverse architectural debt safely. This is a realistic first step. You move one behavior out of the base class, then another, then another. Eventually, the base class becomes small enough that you either keep it for UIKit lifecycle setup or remove it entirely. The goal is not purity, the goal is reducing hidden coupling. One more important lesson. Do not create a protocol just because two types look similar today. Two screens having similar code does not automatically mean they share the same abstraction. Duplication is cheaper than the wrong abstraction. The wrong abstraction spreads. It forces future code to satisfy a contract that should not exist. So wait until the pattern is real. Then extract the protocol. A practical rule. First time, write the code. Second time, notice the duplication. Third time, extract the abstraction. This prevents you from designing a protocol for a future that never arrives. Senior engineering is not about abstracting everything, it is about abstracting at the right moment. Another mistake is creating a protocol that is basically a base class wearing a disguise. If your protocol has 7 unrelated requirements, you probably did not solve the problem. You just moved the inheritance smell into a protocol. Prefer small protocols. One capability, one reason to conform. This is better. Each protocol describes one capability. Now a type can opt into only what it needs. That is one of the strongest benefits of protocol-oriented design. Small promises are easier to keep. Here is the mental model that changed how I review Swift code. Every inheritance relationship is a promise. A promise that subclasses understand the parent. A promise that the parent will not break subclasses. A promise that lifecycle order is respected. A promise that overrides are safe. a promise that future engineers know the hidden rules. Inheritance is not free reuse. It is accumulated obligation. Protocols do not eliminate promises. They make them smaller. Screen Trackable says, "Give me a screen name. I can track the screen." That is a small promise. Much smaller than inheriting a base controller with loading, errors, analytics, navigation, keyboard handling, and view model binding. Small promises scale better. Use inheritance when the type truly is a specialized version of the parent, and you need shared lifecycle or framework behavior. Use protocols when unrelated types need the same capability. Use protocol extensions when there is safe default behavior. Use generics when you want protocol abstraction without existential type erasure. Use composition when behavior needs shared mutable state. And avoid abstraction when the pattern is not proven yet. The takeaway is simple. Inheritance is not wrong. Protocols are not automatically better. The real question is, are you sharing state and lifecycle? Or are you composing a capability? Use UIKit inheritance where the framework demands it. Use protocols where your own domain behavior needs flexibility. And use composition when reusable behavior owns state. If this helped you think differently about your code base, subscribe and drop a thumbs up. It helps this channel reach more working iOS engineers. And comment with how many levels deep your deepest class hierarchy goes. I will reply to a few with refactor suggestions. Next, watch the video on dependency injection in Swift, because this same composition over inheritance thinking is the foundation for clean dependencies. And if you are building a real iOS app and need senior level guidance, visit tony-trejo.com and let's talk.